Welcome to qnawire.
We have this set of triangular plates here with an angular velocity omega, and we need to find what the angular momentum is about the point G. And notice here that we drew a rectangular element within the triangle with the width of dy. So we're going to be using integration to help solve this problem. So we'll start by finding what the area is for each triangular plate. So the area is going to be equal to 1/2 times the length B times the length A. And then we're also going to find what the mass density is for the plates. So the mass density rho is going to be equal to the mass M divided by the area A. And we can then plug in rho, or we can plug in A as 1/2 times B times A, which we can then write as 2M divided by A times B. So now we're going to look back at our rectangular element here, and we're going to need to find what the coordinates are of the centroid of this element in the x direction and in the y direction. So the centroid of this rectangular element on the x-axis is just going to be the length x divided by 2. And for the y-centroid, it's just going to be the length y. So x of c is going to be x divided by 2. And then y of c is just going to be equal to y. So now we're going to write that the area of that rectangular element is going to be equal to dA is equal to x times dy. And we're also going to write that the moment of inertia in the xy direction is equal to x of c times y of c times dA. So we can plug in x of c, y of c, and also dA. So this is equal to x divided by 2 times y times x dy, which we can write as x squared times y divided by 2 times dy. So we're now going to write the straight line equation for the triangular plates. So we're going to write that x divided by b plus y divided by a is equal to 1. And we're going to take this equation and solve for the length x, which is equal to b minus b times y divided by a. So now we're going to find what the moment of inertia is in the xy plane. So I of xy is equal to the integral from 0 to a of 2 times di of xy, which we can plug in di of xy. So I of xy is equal to the integral from 0 to a of 2 times x squared times y divided by 2 times dy, which we can write as the integral from 0 to a of x squared times y dy. So now we're going to take the value of x that we calculated for and plug it into our integral. So this x term, we're going to plug it into our integral. So now I of xy is equal to the integral from 0 to a of b minus by divided by a squared times y times dy. And solving this integral will give us a value of 1 over 12 times a squared times b squared. Now we're going to look at our diagram here, and we're going to notice that in the YZ plane, our moment of inertia is going to be 0, since these plates do not lie within the YZ plane. So I'm going to write that I of YZ is going to be equal to 0. And now the moment of inertia in the y direction is going to be equal to 2 times the moment of inertia of a plate, of a triangular plate. So I'll write that as I of plate. And we know that the moment of inertia of the triangular plate is going to be equal to 1 over 12 times a times b cubed. So we can write I of y is equal to 2 times I of plate, which is then equal to 1 over 6 times ab cubed. So now we're going to find what the mass moment of inertia is in the xy plane. So this is going to be equal to the mass density rho times I of xy. So we plug in rho, and then we plug in I of xy. And this becomes 1 over 6 times m times ab. And we can plug in m, and we can plug in a, and we can plug in b to get a value for this mass I of xy. So the mass is given as 8 kilograms. The length A is given as 0.75 meters, and then B is given as 0.75 meters. And so this becomes 0.75 kilogram meters squared. And we're now going to do the same thing for the YZ plane. So the mass moment of inertia in the YZ plane, this is equal to rho times I of YZ. And we already know that I of YZ is equal to 0. So this then becomes, so mass moment of inertia in the YZ plane is just going to be equal to 0. And next we're going to calculate the mass moment of inertia in the y direction. So this is rho times I of y. So we can plug in rho, and then we can plug in I of y. And this becomes 1 over 3 times m times b squared. So we can plug in m and we can plug in b. So now I of y is equal to 1 over 3 times 8 times 0.75, and this becomes 1.5 kilogram meters squared. So now we're going to write the formula for the angular momentum about the point G. So that angular momentum, we can write that as negative I of xy times the angular velocity plus I of y times the angular velocity minus I of yz times the angular velocity. So now all that's left is to plug in values. So we plug in I of xy, and then we plug in the angular velocity, and then plug in I of y times the angular velocity, and then plug in I of yz times the angular velocity. And so we'll get our final vector components of negative 4.5i plus 9j kilogram meters squared per second.